Okay, given the fact that we have covered probability theory, we've talked about univariate statistics from the perspective of display, calculation, and display of distributions, let's start to talk about statistics. So finally, get into some statistics. We'll talk about measures of centrality, central tendency. We'll talk about measures of dispersion and get into some moments, talk about shape, and statistical expectation. So let's start with measures of central tendency. So the most straightforward and easy to understand is the arithmetic average. I think many of us know about the average. It might also be called the mean. And the calculation of the arithmetic average is pretty straightforward. You simply take all of your data, sum it together, and then divide it by the number of data. This could be the sample mean if we're calculating the mean of an available sample data set. Now there are some cases in which we have access to the entire population, and we are then at liberty to calculate the entire population mean, and we'll denote that as the Greek letter mu. But most of the time we will deal just with the sample mean, which we can denote x over bar. The median is the P50, and of course we just recently talked about distributions, cumulative distribution functions, PDFs, and so we talked about the idea of calculating a percentile. And so the P50, it's natural to realize that it's simply going to be the data value that is at the center of your data set if you sort it in ascending order. So let's take our data, we sort it into ascending order. Here we have 1, 2, 3, 4, 5, 6, 7, 8 data values. This is the lowest value, this is the highest value. The P50 would be the value in the middle. Now, this is a bit tricky. It's an even data set. We have 8 values available, so we effectively have 2 data values in the middle. And so the convention is simply to take the average. So if n is even, we have an even number of data, we will simply take the n divided by 2 index x plus the x of n divided by 2 plus 1, and we'll go ahead, in other words, this one and then this one here, you're taking the integer of it, and you just divide it by 2, so you're taking the average of those 2 data values. If you're fortunate enough to have a data set that has an odd number of data, then you effectively have a data value in the middle, and you can just pick that as the P50, which is this right here, the value at the index, number of data plus 1 divided by 2. So if we have 7 data plus 1, that would be 8, divided by 2 would be 4. 1, 2, 3, 4, the 4th data value, its index will be the P50. The mode is the measure of the most common value. And so if we were to look at a histogram in which we bend our data up, we could look for the bar for which we have the highest frequency. This is a histogram with the frequencies denoted as numbers here. We've normalized it so it effectively is a binned PDF, probability density function. So we have the probabilities shown here for each one of these bins. So this bin here would be the mode. In the case of a categorical variable, it's simply going to be the category for which you have the highest proportion. This is facies. Limestone would be our highest, our mode as far as our various categories go. So here we have a nice little example. We have 1, 2, 3, 4, 5, 6, 9 data values available to you. They're all fraction of shale from cores. And go ahead and calculate the mean, the mean, the median, sorry about that, and the mode. So go ahead and calculate that. I'll show you the answer in 3, 2, 1. Okay, so this is pretty straightforward. I cooked it a bit. The sum of all the values, there's 9 of them, is 90. So I didn't want to force anyone to have a calculator in class. So that would simply have a mean, arithmetic average or mean of 10% of fraction of shale. The median value, I'm correcting as I'm going here, just sort them and take the 5th value. Since you have 9 data values, you just simply go n plus 1, 10 divided by 2. You take the 5th index value if they're sorted in ascending order. And so 1, 2, 3, 4, 5, it's 8%. Then for the mode, you take the most common value, and so we have 3 values that are 8%. And so you'll take that as your mode. You could also use some type of binning if you were to do a histogram display and so forth. But here we'll just simply say the value which is most common. So we haven't talked about parametric distributions yet, but let's go ahead and take a look at the Gaussian PDF shown right here. We can see the nice symmetric shape. It's got a single mode here, or a high value or peak here. And if we look at a distribution like that, the mode, the median, and the mean are all going to be the same. It's got the one peak in the middle, it's symmetric, and so we would expect them all to be equal to each other. And so if somebody asks you what's the central tendency of this distribution, it's pretty straightforward to answer that question. It's all the same. Now if you take a skew distribution, we'll talk about skew shortly, like the log normal distribution shown here, we find that the mode is less than the median, which is less than the arithmetic mean. And so if somebody asks you what's the value of the value you should use for central tendency, well, it's going to depend on the purpose of what you want to accomplish with that value. And we'll talk about that shortly, but it's not so straightforward. There's different measures, and it'll depend on which measure you choose to work with. Here's an example of a non-parametric distribution. We worked with a bunch of those, and so we calculate the CDF. It's very steppy. It's got a lot of steps in it because it's not a lot of data, so you can see the individual steps. And we can go ahead, just like we've done before, where we do the inverse operator on the cumulative distribution function by taking the cumulative probability value and coming across and coming down to calculate the P50 or the median value. And of course we could take all the data values, pull them together and calculate the mean. And we could also identify the mode directly from the histogram shown here with the frequencies, and we can see that there is a specific bar or bin that has the most values. Now, as I just mentioned, you might ask the question of which central tendency is the right one. And to illustrate this, let's look at the fact that we have even more, not just the arithmetic mean, we have the geometric mean and the harmonic mean. And so let me just explain them, and then I'll get to why we're showing them on the next slide. So we got the geometric mean. It's going to be the product sum, or sum product of all of the data values. And then you're going to take that to the power 1 over the number of samples. That's the geometric mean. Commonly applied or seen as a good central measure within the Gaussian log normal, I should say, distribution. In fact, it's very useful because as the log normal distribution shrinks its variance down, it converges to the geometric mean. Now we're going to talk about variance and dispersion shortly, but we'll just give that comment right now and let that sit. The harmonic mean is shown right here. You're taking the number of samples and dividing it by the sum of 1 over all of the sample values. And so what's very interesting is that the harmonic mean, in fact, would be a good calculation of the effective permeability given the permeability in a bunch of equal thickness beds going along here, and where you're flowing perpendicular to those beds. If you were to calculate the harmonic mean of even slices or equal thickness slices moving down through this with different levels of permeability, that would be a pretty good measure that you could assign to this entire block and say that's the effective permeability over that block. A form of scale up, of going from individual beds to actually now talking about this entire block and getting one effective value for that. So that's very interesting. And if you wanted the permeability along the layering, the arithmetic mean, so if we were flowing along the layering in the other direction, the arithmetic mean, or arithmetic average I should say, would be the best measure to use. So there we have a case where the measure of central tendency could be selected based on the concept of averaging for scale up of an effective property given the physics of flow. And so that's interesting. So there are cases in which the measure of central tendency, we can understand which to use based on the physics of the problem. So there's a more general type of description of this. It's the power law averaging of effective permeability. And so the concept is shown here of power law averaging. We have the data values, I equals 1 through n. We have, of course, here what looks like an average, but we have it raised to a power. And then the entire thing is taken to 1 or the inverse of that power. And that's how we're calculating the effective property. So if we had a volume, V, and we integrate over that volume raising the permeability to a power, and taking that entire that integration over the volume divided by V, and we were to raise that to 1 over, or the inverse of the power, that would be a method for calculating effective permeability over a block, a scaling of smaller measures of permeability to account for flow directionality. Here's the power law relationship. Here's the case of volume integration for calculating or upscaling permeability. And what's very powerful about this is that, as we mentioned before, if we use the harmonic average, that's actually what we'd expect if we flow across the layers. If you take a power of -1 and substitute it for P, you can see immediately that you get this equation back. The arithmetic average is for if you're flowing along, concerned with effective permeability along the bits. And if you take 1 and you put in this equation, you'll see this simplifies, well, specifically over here, it'll simplify down, and it just becomes the arithmetic average. So you can see how you can move from -1 to +1, harmonic average, to arithmetic average. And by varying the power, you can actually explore the space in between. What's very interesting, if you put a power of 0, you actually get the geometric average. That's a bit of a complicated proof. We won't go through it right now, but I do provide a reference, and I could, if anybody wants, a link directly to that paper. For my students, I have placed it on our internal server. Now that we've talked about measures of central tendency, let's talk about measures of dispersion. And the point is this, is that you could have a distribution with an average of 100. Okay, so that distribution could be permeability, it could be whatever it is. And you could have another distribution in blue that also has an average of 100, but they have totally different levels of spread. And that would be important. If we just think about average or central tendency, we're missing a lot of information about how our property is distributed. And so we need some type of measure to be able to quantify that. And so the variance is the most straightforward measure to consider for that. It's very compact, it's very useful. So the population variance is the average square difference from the population mean. And so if we take the average of all of the square differences between all the data values and their population mean, that would get us the population variance. Now, it turns out most of the time we don't have access to population statistics. We don't have the population mean. We can't directly, we have to estimate the population variance with a sample variance. Denoted by S squared instead of sigma squared. This is the sample variance. It's the same equation, except for we're using the sample mean. And then we account for the fact that we have estimated the sample mean by subtracting 1 from the n. This provides us an unbiased estimator. Yeah, so one way to think about this is the concept of degrees of freedom. We had n data available, but we had to estimate the mean, so we take 1 off for the fact that we had to estimate that. Now, it turns out that variance is kind of a strange unit. If I calculate the variance of porosity, my units in fact are percentage squared. Or if I calculate the variance of permeability, it may be millidarcies squared. And so that's strange. The units may be very large or very small, depending if you're below or above 1. And it's kind of hard to conceptualize. But if you take the square root of variance, you get the standard deviation. It has the added benefit of being in the units of the actual data values, and so it's a little bit more intuitive, so we often use standard deviation. When we get into hypothesis testing and so forth, we'll use it a lot to understand sampling, uncertainty distributions, and so forth. Now there's other measures of dispersion, not just the variance, sample, and population variance. We could use the range. It makes a lot of sense. You could calculate the P100 and the P0, the ultimate min and max, and take the difference of them, and that would give you the overall spread of your data set, right from the very minimum to the very maximum. Now, that's very useful, and I've shown an example right here, but there's problems with that. The min and max are the most unreliable measures. Once again, we sampled 1/1,000,000th of the subsurface, often volumetrically. What's the chance that we observe the ultimate minimum and maximum values? So it's very unlikely. In fact, you'd imagine that range statistic could be very unstable. And what about outliers? You could happen to have one or two samples that kind of push the min or the max and are not very reasonable, and you're very unsure of them. So it's safer to work with some type of quartiles or quantiles, and let's talk about that. So quartiles. A quartile is just the P25, the P50, and the P75. The interquartile range is taking the P75 and subtracting the P25, and so you're effectively just getting this range right here, P75, P25, the difference right there, 7.8. Very straightforward. Now, we should note here, these were quartiles, but a quantile would be any division of the interval over which you have data values from min to max that divides into equal parts. And so if we're talking about dividing between 0 and 1, is we're working in the cumulative probabilities, then we could talk about, you could have a Q of 4, that would be like your quartiles. You could have a Q of 5, and then you'd be going P20, P40, and so forth. You could have a Q of 10, and then you'd be going 10, 20, 30, and so forth. And so you could just decide on any quantiles. And so some example quantiles, quartiles, deciles, percentiles. So now your measure of dispersion is literally going to be a table. You calculate a set of these quantiles and you just write them out. You're like, well, the P25 is equal to this, the P50 is equal to that, and so forth. And so you could report anything you want to report. Quartiles with interquartile range is very common, P25, P50. A lot of times, this should be P75, sorry. A lot of times you'll see P90, P50, P10. That's not exactly a quantile, but in industry, the P10 and the P90 are widely accepted to be the end members of the low and the high case, and the P50 is often used as the central case. Of course, it's not equal to the mean if the distribution is not symmetric, but it's frequently used. What's interesting is that for Dijkstra-Parsons calculations of flow heterogeneity based on the permeability distribution, they actually use the P50 and the P16, which is kind of interesting, and there's an explanation for that. We'll talk about that when we get into heterogeneity, but we can pick whatever we want to work with. It makes sense that you're not going to pick, the reason we like quartiles, they should be really well behaved. They're in far enough that we have a bit of mass, quite a bit of data around us. We're not near the flimsy tails of our distribution, which are really poorly. Things become much more certain as we move inwards. So, P10 does a pretty good job too, but could still be a little bit unreliable. And so we have to make a choice. Okay, most companies do report P10, P50, P90. So if you're working in a subsurface asset team and you've developed a model for oil in place for a brand new reservoir or unit X of project Y, and you report P10, P50, P90 of 130 million barrels, 230 million barrels for P50 and P90 at 440 million barrels, then that's a big deal. That's the target. That's the product of all of your effort for probably months of modeling, mapping, uncertainty characterization, statistics, and so forth, all kinds of integration of data sources. This is what is used to make very important investment decisions within our industry. This is what everyone's looking for. And so this is typically what's being reported up through your management to your subsurface lead, up through your country lead, and so forth, and business unit leads, and so forth. Now, some companies reverse the convention. And so they've decided, effectively, it's like their CDF is flipped upside down. And that's what I'm showing right here. So instead of the CDF representing the probability of any random sample being less than or equal to a threshold, they're saying greater than or equal to a threshold. See, it's hard for my brain to even think that way. Greater than or equal to a threshold. And so they end up with this monotonically declining curve right here. And so you just switch your brain, you just realize that for them, the P10 is good, the P90 is bad, the low case, and so forth. But it's not a big deal. It's just a reversal of the convention. Okay, so measures of dispersion, how do we detect outliers? How do we define them? A very common way to detect outliers is to use a lower and upper fence. And what we do here is it's a rule of thumb where we take the P25 of the distribution and we take subtract from that 1.5 times the interquartile range, and that gives us a lower fence value. Upper fence is just the P75 plus 1.5 times the interquartile range. And so it's an outlier if we're below the lower fence or if a value is greater than the upper fence. And so here's an example right here. We have our data set, the same data set we've been using for a while now. So we already calculated it. We already have the P25 and the P75. Interquartile range is 7.8. Got the calculator out, and we can go ahead and calculate the lower fence, P25, subtract 1.5 times the interquartile range, we get 7.3. Plot the lower fence. Upper fence, take the P75 plus 1.5 times interquartile range, and we get the upper fence and plot that. So what do we do with that? Well, any values that are at or lower than the lower fence, we consider them potentially be outliers. Any values above the upper fence, and we have none above the upper fence, so we'll just look down here. We've got outliers in the bottom. What does that mean? It means look at them, explain them, understand them. There's a variety of things we could do. We could remove them. Now we have to demonstrate that they're erroneous. We can't just decide to just say, I don't like this data, because in fact, it might be valuable. You might actually find out that this is a different phenomenon and something you should understand in the subsurface. And if we just ignore it, that's bad. That could be a bad idea. We can in fact bias the whole estimation. You could transform. After you've explained it and decided to keep working with it, you may decide to use a distribution transform, which will take care of some of the numerical issues that may creep in if you have outliers in your distribution. Probably more common would be to separate them. Pull out the outliers and work with them separately. Once again, they might be something interesting that we should try to understand about the subsurface. Okay, maybe a brand new type of facies or something. Okay, so what about box plots? Well, I like box plots. They're very simple to understand. What you do with a box plot is you're basically just simplifying and plotting a distribution. If you have different classes or categories, you can plot them all side by side in a very compact manner. I could put the distributions on their sides, but it would get noisy. It'd be hard to look at everything. And so let's take estimated oil recovery efficiency for different locations geographically within the world. And so we're going to plot a box plot to summarize the distribution. The median value, that's not a big deal. We know that. P25, P75. We just plot them. We draw a box around it. We put a big solid line in the median. So now we got the interquartile range. We got the median value for a good measure of central tendency. Okay. Then what we'll do is that we'll plot the other ones too. And now we have a nice way to compare. We kind of see the degree of spread in the interquartile range, how it's changing. We can see how the median value is changing. We can also plot the upper and the lower fence and put little bars on them and then connect it with a line, and those are called the whiskers. Box, whiskers. The usual convention is that the whiskers go to the upper fence and the lower fence, but sometimes different plotting programs will use different conventions for the whiskers. Any data outside the whiskers are actually denoted as actual dots for the data values, so you can look at them specifically as potential outliers, try to explain them, understand them. What happened down here? Well, you're in a situation where if you take 1.5 times the interquartile range, subtract it from the P25, you go into negative values. And that's physically implausible, so we'll truncate the whisker at the bottom. If we were to plot the lower fence, it would be down in the negative realm. But that's okay like that. We cannot have outliers at the bottom, and that's the purpose of the whiskers. Now that we've talked about this idea of central tendency, we've talked about the idea of dispersion, it makes sense for us to be talking a little bit about moments. And we're going to just deal with this really quickly. It'll be a segue into skew and kurtosis, but we're going to admit the fact that we're just kind of skimming over it. We're going to only consider population statistics. We're not going to look at sample moments. That's out of scope. That gets quite a bit more complicated. And so let's just go ahead and walk our way through this. Okay, now let's take the first central moment. The first central moment is going to be, by definition, always equal to 0. And how do you calculate the first central moment? You take the average of the difference between the data and the mean raised to the first power. It's the first moment. I didn't even put a 1 there because you don't need it. Okay. Now, with this summation, you can break it apart. And if you break it apart, this part right here becomes the mean. This part right here, because we're just taking effectively the average of the means, or a bunch of means, is going to be equal to the mean too. And the average of the means is the mean. And so we get the mean minus the mean. It's equal to 0. It's more interesting if you take the first moment and you have not taken the central moment. You have not removed the mean from it. In that case, the first moment is just equal to the mean. So I hope you can see that the first moment is kind of trivial. The central one is going to be 0. The non-central one is just going to be equal to the mean. The second central moment is equal to the variance. We're simply going to take all the data values, subtract out the mean, population mean, and mu, and then take the square of that and take the average of that. Summation of all those squares, take the average, that's equal to the variance as we defined it before. That's the second central moment right there. Okay, nothing unusual. Now, if we did not subtract the mean from it, that would just be the second moment, not a central moment. Okay, the third central moment is we're going to take, it's just like the variance calculation, but we're going to calculate all the data, subtract out the mean, and take it to the third power. We're going to cube it. Okay, this gives us the third central moment, and we also know it as skew. And the fourth central moment is kurtosis. And for that, we just raise it to the fourth power. So I hope you can see that we get skew and kurtosis by just increasing the power we use within the variance. And we get that way we get these third and fourth central moments that are very useful to us. Now, I kept talking about central moments, so I subtracted the mean. You could also central and standardize. If you do that, you would be dividing by a lower moment. So in this case here, we have the skew, but we've actually been dividing out the square root of the second moment from it. So, so it can get much more complicated. We'll just stick with this idea of these central moments. So that led us to this idea of skew, which is our third moment. And so what does skew look like? Well, anytime somebody says that something is negatively skewed, what they're suggesting is that the distribution or the thing is moving, that it has a tail towards the negative side. That's the way I think about it. I think, which way does the tail go? And it goes towards the negative side. If it's positively skewed, it has this tail going off towards larger numbers, positive side. So that's skew. That's pretty useful. It's a good measure of shape. If your subsurface property has one of these skews, it's important because you might have the same range, the same min and max, but skew tells you a lot about, do you have a lot of low values or do you have a lot of high values? Kurtosis is also a very interesting measure. It's a measure of peakedness. Peakedness. That's kind of cool. Now, what's interesting, if you calculate kurtosis, remember it was a fourth power statistic, so you're not going to get any negative values in it. In fact, if you do it on the normal distribution, the Gaussian distribution, you get a kurtosis of 3. And so folks who thought they'd make this more interesting or more easy to understand said, well, if we know the Gaussian is going to be 3, let's subtract 3 from all the results and we'll call it excess kurtosis. That way, if you get a 0, you have a normal or Gaussian distribution peakedness. If you have a less than 3, which would now be a negative excess kurtosis, this would be platykurtic. And so that would suggest you have low peakedness. you have what would also be known as fat tails, which is a statistical concept, which means that the tails have higher density than you'd see in a Gaussian distribution, and you don't have the big peak in the middle. Leptokurtic is if you have kurtosis that's greater than 0, excess kurtosis greater than 0, and so that would be very peaked. The tails are thin now, and most of your mass is located more into the center. This is valuable. It's telling you about the overall shape, and also if you imagine these distributions are representing uncertainty, if you have something that's platykurtic, it suggests that your uncertainty, you have a much more chance of experiencing kind of the end members. If you have something that's leptokurtic, it suggests that things will tend to be closer to the center. You won't have as much going on, likely to go on near the min and the max. Yeah, kind of cool, very cool. So this is the skew and the kurtosis. Now, you might find that skew measure kind of counterintuitive, you know, third moment and all, third central moment and all that complexity. And so you might want to use a more simplified, intuitive form of skew. And so Pearson's mode skewness is shown right here. Skewness is equal to the mean minus the mode standardized by the standard deviation. Perfectly okay to use that. We use these statistics to describe things, and if they're more intuitive to you, then that's useful. And to make comparisons too, so it's still helpful. Quartile skew coefficient, look at this, this is wild. Where you have the interquartile range in the bottom, and we've taken apart the interquartile range, we're looking at the degree of symmetry between the upside and the downside here in order to get this measure of quartile skew. Now, what I want to do is I want you to have a chance to play around in Excel to try to calculate all of these summary statistics. So I prepared a data set, porosity sample 1, it's got 40 or 50 samples along a well of depth. It's located in Excel. For my students, it's on our server. For anybody who's not in my class, you can go to GitHub. I put all my data sets on GitHub. You can go to my GitHub Geostats guy. You'll find a bunch of data sets you can play with. And go ahead and download that data set, and then within it, make these calculations. And so first of all, plot the CDF. We talked about that a couple lectures ago. It's good practice, right? So go ahead, you know, there'll be some sorting. You have to calculate with some type of tail assumption the cumulative probability for each of the data values, plot them against each other. Then you can calculate the average, the variance, sample variance, and quartiles using the percentile.exc command. So I've given you actually the Excel commands right here. Then you're going to go ahead and check for outliers, calculate the skew, the command is skew, and the kurtosis, the command is kurt, parentheses, the range of the data. Now you might wonder if you get into this exercise, you're going to find out that there's percentile.exc and there's percentile.inc. The difference is the tails. Because you'd imagine that's going to matter. If you have different tail assumptions, it's going to matter what value is what percentile. And so with the percentile.exc, it assumes both the tails are not known. You notice with the very first data value, you're not a cumulative probability of 0, so you don't have the lower tail. At n, which is the last data, the maximum data value, you're still not at 100%, so it suggests that you have an unknown upper bound too. The percentile INC, you'll see if you take data value number 1, I equals 1, what happens here in fact is you get a 0 for the cumulative probability, and if you put an n in there, you get a cumulative probability of 100%, meaning that you're assuming your min and max of your data set in fact are your tails, your ultimate min and max. Okay, so go ahead and do this. I'll review the answers very quickly in 3, 2, 1. Okay, so I did this, I worked it out. I did it by hand, by doing the counting methods and so forth, but I also ran and did a little linear interpolation, but I did it using the Excel functions right here. This should be similar to what you got. And so if you go ahead, check and make sure you get the same numbers. The cumulative distribution function is shown right here. And when I check the lower fence and the upper fence, I found in fact that there are no outliers. And it was interesting, the skew suggested that we have a slightly negative skew and we are leptokurtic. We have a distribution that's a bit more peaked than the Gaussian distribution. So what I'm going to do is I'm going to stop there and I will record a discussion about the statistical expectation right away and include that. But I think we've done a pretty good job of covering univariate statistics, talked about measures of central tendency, measures of dispersion or spread of our data, and also measures of shape, even up to the concept of the moments of our distribution. I hope this was helpful. As always, if you have suggestions for how we can improve this, I'm always happy to address that. All right, take care.